So I wanted to do one quick pulse of closed loop pulse propulsion real fast. Um, kind of have to create the system so that it um, kind of has this geometry. So what happens is when you push these springs off, this will go up, the ropes will come around here, swing around here, and a little bit will kind of, kick around here, adding a little bit of angular momentum. And you'll see it when it kind of comes through here. So just think about a ball going around a tether ball going around a pole, and that's what that's doing. So that's just giving it a little bit of an extra kick. But when it does it, it's going to kick it, you know, well, you'll see. So anyway, we got the springs. I got different tensions on the springs. So this one here is really strong. Springs like 6 newtons per meter, and it pushes it way out. So springs 0.57 meters, and then this one here is 0.95 newtons per meter and only point. So these only go out short way, so it's going to push it out this way. This is going to push this out this way, the exact same setup. And these things are going to go out that way. And we're going to go real slow. So let's go really slow. So you can kind of see how it launches off. This is going to be the equal and opposite reaction. So it's going to go down this way. And these are going to go out. These are going to go out. And this is going to go down. This weighs material. I dropped everything down way low. So I'm going to kick that up just a little bit, 0.5. So it's really light. It's only, 0.4 kilograms. These balls are lighter. So it's 0.07 kilograms. So these are light. So we're just putting a bunch of energy into it with the springs. Everything's stopped right now. These are just ropes that are on the side. They can be chains, ropes, doesn't really matter. But it does have to have freedom of movement that's not directly tied. These almost have to be like two separate systems, even though they're connected and it's a closed loop. What you have is when this fires here and this fires here, you get the equal and opposite reaction. That reaction's done. You can't undo that reaction. Then that reaction is actually working its way through the system. And just watch. So we're going to go real slow. You see how this pushes this way, this pushes this way. Everything's doing exactly what you want it to do. And I do realize this is a two-dimensional model. So in 3 dimensions, this would be so hard to achieve. It's ridiculous. Just because you would have to get everything completely aligned into a two-dimensional frame of reference. But it's kind of doable. You use okay, so yeah, you can see that's coming around. Let's go ahead and put the fit arrows to the screen, and you can kind of see. So this is doing exactly what you'd think it would be doing. This, after these jumped up, this is pulling it this way, and now everything's starting to come down. This one here isn't going to make it to swing around, so we're not going to get that little kick. But this one here should no. Let's speed it up a little bit and see what we got now. I was hoping for a little bit more of a kick around. We'll probably do it on the next time around. So, boom. Let's show the arrows. There we go. Yeah, so, okay, so you see now we're going to get this little bit of a kick. Boom. Right? There's now slightly more energy in the system because of the angular momentum. Watch, it's going to happen again. See, this one's too far up, so if I extended the rope out, it would do it. But this is, if you look, you can kind of see this doesn't really have enough momentum in it to stop this bigger platform. It just doesn't have enough mass. So watch what happens. We're going to speed it way up now. So as you can see, this is going to come around. Everything's already moving in that direction, right? So now it's going to get another kick in that direction. And this one's going to be impossible to pull those two going in that direction. You can already see this thing has already broken free of the two-dimensional center of mass. This is not a three-dimensional. There we go. Boom. And you're done. Like, you're going to get that extra whip around kick. It's going to go in the same direction, and you're just done. Now, this might do something. Slow it down a little bit. But now everything's in alignment. There's no going back. This is never going to swing back around and come right back into this position. It's just going to be gone. So that's closed loop pulse propulsion. As you can see, in reality, you are not going fast. It does not appear like you've done anything at all. It doesn't look like you're moving. Well, just a little bit, like drift. It's just a drift. And that's the point. It's just creating a drift from your center of mass because you have to account for all the energy in this system, and that's all this program is doing is just tracking the Lagrangian. I mean, it's just following the energy. There's you can see the velocities, right? It's everything's going in the right direction. Any angular velocities, that's just the shit spinning. This thing's not even spinning a little bit, right? But again, it's not spinning in the same center of mass, right? It's already. Let's go way out of here. So you can see it's drifting away. It's never going to go back into its position. It just can't. The energy got kicked into it at a different vector than the equal and opposite reaction, and that's what it takes. You have to cancel the energy. It's not about, there's no such thing as negative energy. No such thing. It's just, I mean, dark energy, sure, we can play that game, but there's no proof of dark energy, and this is not it. So, this will never go back into its frame of reference. If you reset the system, you can do it again. You can get addition. Again, it's going to be chaotic because nothing is controlled. Nothing is pointed in a direction. But as you can see, this is never going to flip back around. And it can't. It's just, again, it's broken free from its two-dimensional frame of reference. Now add a third dimension to this, and again, now you're spinning around the z-axis, and you're just not going anywhere. So this is why they're not breaking out of their center of mass in space, because you have a third direction you have to account for. But you get things like the Jacobic effect and stuff like that that can add in additional energies. And if you can harness that and direct it, that's movement in space. So that's what we're looking at.